Okay. So, um, so welcome to the third TA session in this course, Principles of Signals and Systems, offered by NPTEL by Professor Aditya Jagannathan from IIT Kanpur. And just again a small confirmation. You can hear me, right? Yeah, you can just
Yes,
tell
sir.
anyone. Yeah, okay, thanks. Okay. All right. So basically, as a very quick introduction about myself, my name is Yashvanth, and I'm presently a PMRF Ph.D. student in the 5th year at the Department of ECE at IISc Bangalore. And I'm advised by Professor Chandra Murthy, and who is also with the Department of ECE at IISc. My research interests lie in signal processing and applications of signal processing to wireless communication systems. Presently, I focus on a cutting edge technology called intelligent reflecting surfaces for 5G and beyond wireless com. If you have sessions that we have, and if you want to ask me anything offline, please feel free to contact me on this email ID, and you can know more about me, the kind of research works that I do, and my about my profile in this link here shown here, website. All right, so the topics covered for week 3 include some systems and types of systems, continuing from week 2, and discrete time systems in particular. We will look at characterization of the impulse response of discrete time systems, and categorization in terms of stability, memorylessness, and etc. And finally, introduce Laplace transform. Okay, so that's basically the topics for third week. So, um, as before, we will begin this class session with the part 1, which is to quickly summarize the lectures from week 3. So basically, the first lecture started with differential equation based description of an LTI system, right? So basically, what it says is that any LTI system, the input output relation of any LTI system can be represented by what is called a differential equation. Okay, that is, you can always relate the output as a function of the differential equation, differentials of the input. This is basically a differential equation, both output and input. Okay, this is also called as linear constant coefficient differential equation. Okay, let me just write it down. Okay, this is just not differential equation, it's called linear constant coefficient differential equation. L stands for linear, next T stands for constant, this C stands for coefficient, and DE stands for differential equation. So what does it mean? It just why is it called linear constant coefficient? Because all these AMs and BMs are basically linear constants. Okay, it's a linear differential equation, and it is moreover constant coefficient. That's why AMs and BMs are basically constant coefficients, and it's a linear differential equation. So that's why it's called a linear constant coefficient differential equation. This is more a very rigorous term, but you can always say differential equation, no problem. What this says is an LTI system can always be represented or characterized by a linear constant coefficient differential equation. Okay, and what is the solution to such kind of differential equation? So solution y of t is always, it can be decomposed as two parts. One is called the yp of t, which is a particular solution of the of this differential equation, and yh of t, which is a homogeneous solution. Okay, so these are the two types of systems. And linear system, for a system to be linear, you need to consider that the all initial conditions are equal to 0. If for a system to be time invariant, the system has to be at rest at the initial state. That is, it should not give any output at t equal to 0. Okay, initial means whenever you start observing this properties or output of a system, that is at t equal to 0, there should not be any output. Okay, that is, it should be at rest. The rest system has to be at rest. Okay, that's what is given here. Basically, if your input there is no input till time t naught, then output should also be 0 till time t naught. Okay, that is, it should be at rest. Rest means it is not giving any output. So this is called, if that system obeys that, then it will be a time invariant system. Okay, so that's just some background, just to know that, okay, you can represent LTI using a differential equation, just as a fact. But we will later, when we go for transform theory, you will see that this differential equation based representation of a LTI system comes very handy, because what happens is the Laplace transform of differential is just the of product of s times y of s, where s is a Laplace variable. So we will see such properties later, where you can basically, a differential equation can be represented into a much simpler form in the Laplace domain, when you take the Laplace transform, and using that, it becomes very easy to find the output for any given input of any LTI system. So that way, maybe in the time domain, this is not a very useful, it is still useful. You can always solve for a different, for example, you can given x of t, these AMs and BMs are determined using the impulse response. So you can always solve for the differential equation and find what is the output y of t. But that's like a little tedious job. You need to solve for a differential equation. So maybe in the time domain, it is not that attractive. But it turns out that this kind of a representation becomes very useful if you transform the problem into into another domain, say Laplace domain or Fourier domain, where the solution becomes where finding the output becomes very much simpler if you adopt a differential equation approach. Okay, for now, just know that for an LTI system, input and output can be related using a differential equation. Now, going to discrete LTI system, right? That is basically same as LTI, but now the system only processes discrete signals. That is, it takes a discrete time signal as input, and gives discrete time signal as an output. So these are called discrete LTI system. They also have another special name called linear shift invariant. Why? Because in LTI, what is T stands for? Time invariant. Here it means shift invariant. That is because any delay. See, what is the meaning of time invariance? F x of t minus tau should give y of t minus tau. Now, in terms of discreteness, it is nothing but x of n minus n naught should give an output y of n minus n naught. So essentially, it's a shift by a unit of n naught, because n naught is an integer. It's a discrete integers at which you define your signals, right? That's why this L you can also call LTI as LSI, linear shift invariant system. Okay, that is just another way to denote an LTI system when it is a discrete time system. Okay, so again, it turns out, like in LTI, continuous time, discrete LTI, that is an LSI system, can also be uniquely characterized by what is called an impulse response. Okay, that is what is impulse response? You give, if let's say there's a system T that takes x of n as input and gives y of n as output. Okay, now what you do is, now put x of n equal delta of n, right? You pass a discrete impulse function as input. Whatever output you get, that is basically called that is called the impulse response, and this is called a discrete time impulse response, because this is a impulse response for a discrete time system. So it's called discrete time impulse response. Okay, similar to continuous time, the output of any given by the convolution of the input discrete time signal and the discrete time impulse response. Only thing is, though, earlier you recall that there was an integral for convolution, but now the integral is replaced by summation, because we only have discrete time signals, not continuous time signals. Okay, so rest of it, everything remains same. Similarly, when a system is memoryless, right? If you recall, similar to what we had for continuous time, right? That is, what is memoryless? The output will only depend on present input, will not depend on past or future input. That is what that means. The impulse response at h of n should only take value when delta of n, some scaled version of delta of n. Why? Because at the h of n should only depend on nth interval, the signal n. It should not depend on n minus 1 or n plus 1. That's where delta of n will ensure that it has 1 only when n equal to 0. That is, at the current time instant, you basically get the output. The output will depend only on the current time, the input given at the current time instant. That's why it depends on the current input. That's why for a memoryless LTI system, your impulse response should be a scaled, k can be any number, k can be any real number, a scaled version of Del discrete impulse function. Now causality. What is causality? Similar. What is causality? That is your input. The impulse response should be your output should only depend on present input and past input. It should not depend on future input. That is, and in terms of the impulse response, the characterization is that whenever your for any negative number n, your h of n should be equal to 0. Then if your impulse response is equal to 0 for negative values of time or negative values of n, then that is an LTI system which is also causal in nature. What is BIBO stability for a discrete time LTI system? Similar to continuous time. So continuous, you remember this was the definition of our BIBO. That is, you integrate your mod of h of t from minus infinity to plus infinity, and this number should be strictly less than infinity. It should be a finite number, or the impulse response should be absolutely integrable. Same thing applies for discrete time also, only except that the integral will become summation now. So the impulse response should be absolutely summable. Then this system is a stable system, BIBO stable. Okay. Now it turns out that for a discrete time LTI system, the signal x of n is equal to z power n. So this is, let's say, define as signal x of n is equal to z power n. This signal or this function is called the eigen function of the discrete time LTI system. I will come back to it today, time permitting. Why it's called eigen function? For some of you who have done matrix properties, what is an eigenvalue of a matrix? An eigenvector. So if you have an equation Ax equal to lambda x, where x is a vector, A is a matrix, and lambda is a scalar, then lambda is said to be the eigenvalue of A, correct? And x is the eigenvector of A, corresponding to the eigenvalue lambda. Similar notion only it applies here also. What is what? So basically, what it is doing, you take a vector x, you transform, you multiply this with A, you will get back the same vector x, but with scaled version of x. That is the meaning of the eigenvector eigenvalue. Same thing only here also. What you do, you give x of n as input to the system. If the output is lambda times x of n, then this x of n is said to be an eigenfunction of the system. And it turns out that for a discrete time system, x of n is equal to z power n is an eigenfunction. That is, if you give z power n as an input, you will get lambda times z power n as the output. That is, the output will be a scaled version of the input. For whichever input, the output is a scaled version of the input. Those inputs are basically called the eigen signals for that particular system. For every system, it can vary, but in general, for an LTI, discrete time LTI system, x of n is equal to z power n is an eigen function of the system. So where will we use these properties? Maybe time. So let's say there is a system and we don't know the characteristics. Let's say we want to find the impulse response. Now, what is a easy way to find the impulse response? They make use of eigenfunctions, because the z of n, if you pass it as input, output is scaled version of z of n. That means the scalar should be capturing the impulse response. Okay, because anyways input, I know that output will be scaled version of z10, and the scaling can happen only because system. So like this, they use some very clever tricks in order by using eigenfunctions to characterize the impulse response of system. So that is one application where an eigen signal is useful. Okay, similar to continuous time LTI system, for a discrete time LTI system, the input and output are related by what is called a difference equation. Okay, this is also the same acronym. It's called a linear constant coefficient difference equation. Same thing, but instead of this D standing for differential, it now stands for difference. Okay, only difference is that instead of dn by dt, this you replace by y of basically you see what was there in the decision. You take the mth order differential of y of t. Instead of that, you do y of n minus m. That is, you delay by m instead of taking the derivative with respect to m. If you do that, then the differential will become difference. Okay, you see here, yn minus m. So d power m y of t by dt power m has now become y of n minus m. Not power differential, but it is a difference. Okay, that's the only difference between a differential and a difference equation, and your summation will all be the same. Okay, so this is a linear constant coefficient difference equation. So any discrete time LTI system can be represented using a difference equation. So this was about systems. Now moving on to Laplace transform, very important transform. In this course, we'll see a lot of transforms. We'll see Laplace transform, then Fourier transform, then something called Z transform, then we'll see something called discrete Fourier transform, discrete time Fourier transform. There are so many transforms. That is the goodness about signal systems. Why so many transforms? Each transform will help you to simplify your problem in different ways. Okay, suppose as I give you a problem. Now, which transform should I choose so that that problem can be solved easily in the transformed domain? You solve it in the transformed domain and then bring it back to the original time domain. Okay, so that's why transforms are very useful tools in order to analyze the system properties and also in order to process a signal. For example, x of t, if I give you two signals x of t and y of t, and if I ask you to perform x of t convolution y of t, you remember this was basically integral. It's too much, very difficult. You need to carefully integrate, compute the integration and do all those things. But it turns out that if you transform this convolution into some other domain, the convolution can be reduced to two steps. So you can perform the same signal processing. You process a signal with in a simplified manner if you transform the signals into another domain. That's why transforms are very, very important and very useful. And that's why we study them in signals and systems. Okay, the first transform in this course is called Laplace transform. So basically, what in Laplace transform, the high level idea is that you represent a given time domain signal x of t in the Laplace domain. Okay, you convert that, you take x of t. So this is the definition of Laplace transform. You take x of t, multiply by e power minus st, and integrate it from minus infinity to plus infinity with respect to t dt. And now this is a function of small s, right? So this is capital X of s. So x of s is said to be the Laplace transform of x of t, small x of t. So I denote this by capital S. Okay. Now you see this s is a complex number. Okay. So you can represent s as sigma plus j omega, where sigma and omega are real numbers. Okay. And in terms of notation, we say that if capital X of s is L of x of t, that is, to take the Laplace transform of x of t is denoted as x of s. Or you can also use this notation. You take x of t, put an arrow mark and write L on top of that and write capital S x of s. That means the Laplace transform of x of t is x of s. Okay. Now, very important, you see how the definition of Laplace transform, it involves an integration. Now, this integration should converge, right? It should be less than a finite number. It should be a finite number. Only then this is a useful number. If you get infinity, what is you can't do anything much. So this Laplace transform is very useful only for those values of s where this integral converges. That is, it is less than infinity. Okay. So basically you need to look for those range of the smallest, the Laplace variable, so that the integral in the definition of Laplace transform is converging to some finite number which is less than infinity. Okay, so that basically defines what is called the region of convergence. Okay, that is, I am not interested in finding the Laplace transform of the x of t for all possible values of s. It is okay if I only characterize the Laplace transform in the region of convergence of the Laplace transform. And the region of convergence will depend on what is basically x of t. For different input signals x of t, you will have different regions of convergence of the Laplace transform. Okay, so that is basically about region of convergence. So basically the Laplace transform is always accompanied by two quantities. One is the value of x of s. The other is the range of s for which x of x is well defined. That is converge. That is, it has two components: the Laplace transform and the region of convergence. So if I say Laplace transform, you need to always give me two things. For any x of t, what is capital X of s and what is its ROC, region of convergence. Unless you tell me both, I cannot do anything. The Laplace transform is no useful. I should have the knowledge of both of them. Only then you can do some meaningful operation over x of t. Otherwise, it's of no use. Okay, so basically what is ROC? ROC is a region on S plane. S is a complex number, right? So I told you S is equal to sigma plus j omega. So you can always write, make x axis as sigma axis and j omega axis as a y axis. So the entire plane is what is called an S plane. Okay, and what is region of convergence? The region on this S plane where the Laplace transform converges. That is, the integral is less than infinity. Okay, as an example, let's take an example. Let's say x of t is equal to e power minus alpha t into u of t. That's the given input signal I have. Now I want to find the Laplace transform of this signal x of t. Now what is the definition? Definition is nothing but integral x of t e power minus st dt from minus infinity to plus infinity. Now what you do, you substitute for x of t as e power minus alpha t into u of t into e power minus st dt. But now u of t is positive only for positive values of t. So I can, and in the positive values of t, it is equal to 1, right? So I can replace this integral by 0 to infinity e power minus alpha t into e power minus st dt. Because u of t is 1 in this integral. In minus infinity to 0, u of t is 0. So this integral will go to 0 in the negative t domain. That's why I have made minus infinity to plus infinity as 0 to infinity. Now, you see, let's maybe write down a little more. So what is this? This is nothing but integral 0 to infinity e power minus of s plus alpha t dt. And what is this? Is nothing but e power minus s plus alpha t by minus s plus alpha from 0 to infinity. And this is nothing but 1 by s plus alpha. Only if, when is this true? Only if s plus alpha is greater than 0. Is it right? Because if this is not, if the s plus alpha is not positive, then e power, this is a negative number, and when I put t is equal to infinity, this will become e power plus infinity, which will make it go to infinity. So the Laplace transform will be not converging, it will diverge to infinity. Therefore I need this s plus alpha to be a positive number. That means you can show that this is equivalently saying that the real part of s should be greater than minus alpha. Okay, if this happens, then the Laplace transform is given by 1 by s plus alpha. Otherwise, if this doesn't happen, this is not the expression. It'll go to infinity. Okay, therefore, if someone asks you what is the Laplace transform of x of t, you should say that it is equal to 1 by s plus alpha in with ROC given by this. That is, real part of s means what? Sigma. Sigma should be greater than minus alpha. So you draw sigma is equal to minus alpha axis, and everything towards the right of this y axis is the region of convergence. Okay. Can anyone confirm if everything is clear till here?
Sir, what happens when it is less than minus alpha?
What will happen if it is less than minus alpha? In this region, what happens? This here, you see, that means what? S plus alpha is a negative number, because if I say that S plus alpha is less than 0, right? That's what you're saying. What will happen less than? That means this guy will become negative number, and there's always another negative here. So negative times negative will become positive. And I'm making t to go to infinity because of the limit in infinity. That means it becomes e power infinity, which will go to infinity. But I don't want Laplace transform to go to infinity. Otherwise, because it's not useful in that region. So Laplace transform, it diverges. It does not exist. It goes to infinity. Is it okay?
Okay, sir.
Yeah. Okay. Another very important property, maybe in the next class you will see the importance of this property, is that two different signals can have the same Laplace transform, but their ROCs can be different. So that is, if I say x1 of t and x2 of t, both can have the same Laplace transform x of s. But what will make them different? Their ROCs will certainly be different. ROC1 and ROC2 both will not be equal. So that means it says that you cannot just have the Laplace transform and say this is a Laplace transform of a signal. You can have multiple signals which will have the same Laplace transform. So you need to specify the ROC also if I want to uniquely say that this is a signal for which I'm computing the Laplace transform. Okay, so you need to specify both Laplace transform along with the region of convergence in which the Laplace transform is defined. Okay, so standard Laplace transforms. If I take x of t is equal to delta of t, this is the impulse function, then you can show that this x of s, a Laplace transform, will be equal to 1. And what is the ROC is everywhere. That is the entire S plane. So you have sigma, you have j omega. The entire plane will be the ROC. That is everywhere it converges. The Laplace transform exists everywhere and it is equal to 1. If you take unit step function, right, that is u of t means it goes to 1 at t greater than or equal to 0. And before that, it is equal to 0. If for this continuous time function, your x of s is given, Laplace transform is given by 1 by s, and when the ROC is such that real part of s is greater than 0. That is, if you draw the j omega axis, j and sigma and j omega axis, everything towards the right of j omega axis, right? Because real part is positive in this. This is the ROC in which Laplace transform is equal to 1 by s for unit step signal y of t. I think these were derived in class. One more very important thing, okay, Laplace transform is defined for continuous time signals. So the entire Laplace transforms theory, we will only look at continuous time signals, not discrete time signals. There is another transform, a counterpart similar to Laplace transform. For discrete time signals, we have something called Z transform. Okay, that is the equivalent of Laplace transform for discrete time signals, and that we will deal little later in the course. For now, we will now for as far as Laplace transform is concerned, we will now stick with all continuous time signals. Okay, so this was like the quick summary of the lectures from week 3. There are any doubts, you can ask me now. Okay, so I don't see anyone asking question. Okay, then let's get started with the second part of the session, namely on some tutorial, some problem solving sessions. Okay, so the last time itself we introduced convolution integral, but we did not solve questions on convolution. It turns out that convolution is very, very important to signal systems, and you need to be comfortable in performing the convolution operation. So we will do some quite a good number of problems on finding the convolution of two signals. Okay, so the first question starts with convolution only. Question is as follows: perform convolution of the following signals. Okay, so you have the first signal is x1 of t is equal to e power minus 2t u of t, and x2 of t equal to minus 5t u of t. Where what is u of t? U of t is nothing but it takes the value 1 if t is positive, it takes the value 0 if t is negative. Okay, that is unit step function. Fine. This is the question. So basically what I'm asking is y of t is equal to convolution x1 of t convolved with x2 of t. What is the value? This is the first simple question we'll solve now. Okay. So what is it? Go apply the definition. Answer. So basically your y of t is equal to x1 of t. You need to find convolved with x2 of t. Now what is that? Just apply the definition. This is nothing but integral minus infinity to plus infinity x1 of tau x2 of t minus tau t tau. This is a by definition of convolution. If you remember, the convolution integral is defined as like this. Minus infinity to plus infinity. What is x1 of t? X1 of tau is nothing but e power minus 2 tau into u of tau. What is x2 of t minus tau? E power minus 5 t minus tau into u of t minus tau. Okay, just Same way, just variable alone you substitute differently here. Okay, so let's do that. E power minus 2 tau into u of tau into e power minus 5 into t minus tau into u of t minus tau d tau. Okay, now what is u of tau will be what? Will be positive, or will take a non-zero value for tau greater than or equal to 0. Okay, that means what? And similarly, u of tau is equal to 0 for tau less than 0. That means you need not consider the entire range of integration. You can just consider from 0 to infinity e power minus 2 tau into 1 into e power minus 5 times t minus tau into u of t minus tau d tau. That's because what it is, I just u of tau takes a value equal to 1 when tau is positive, else it takes a value 0 when tau is negative. When it takes a value 0, the entire integrand goes 0. So in the negative limit of tau, you don't have anything. It's a 0 value. That's why it's enough if you consider this a positive value, positive range of your tau. And in positive range of tau, your u of tau is equal to 1. That's why it becomes like this. Now, similarly, let's look at the second term, u of t minus tau. Now, u of t minus tau is equal to 1 if t minus tau is a positive number, or tau is less than or equal to t. And similarly, u of t minus tau is equal to 0 if t minus tau is less than 0. That is, if tau is greater than t. That means, what does it say? If you should not consider the integral all the way from 0 to infinity. You should only consider if from 0 to small t, in which case u of t minus tau is equal to 1. When tau exceeds a small t, then this u of t minus tau will be 0, and that will make the entire integrand go to 0. That means this can be written as 0 to t e power minus 2 tau into 1 into e power minus 5 times t minus tau into 1. Do you agree? Is it okay? Can anyone just unmute and say if it's okay? Yes. I didn't hear anyone saying anything. Can anyone unmute and tell if this is fine till now?
Yes, sir.
Okay. So now it's a matter of just computing the integral. So let's do that. There's nothing but 0 to t e power minus 2 tau into e power minus 5t into e power 5 tau d tau. So it's a variable in tau, so e power minus 5t is a constant, so take it outside the integration. This becomes e power minus 5t integral 0 to t e power 3 tau d tau, which is e power minus 5t e power 3 tau by 3 from 0 to t. This is e power minus 5t into e power 3t minus 1 by 3. Or, yeah, I think this is enough to represent. For what values of t? Only for t greater than 0. Why? If t is c, the integration is from 0 to t. That means t has to be positive. If t is negative, that means there is no integral. You cannot define integral. T has to be positive in order for this integral to exist. Right? Because it's a lower limit, upper limit. Upper limit should always be greater than lower limit. If upper limit is less than lower limit, there is no integral. So it's by definition 0. There's nothing you will get. You cannot do, the integral doesn't have any non-zero value, proper value. So it is 0. So this is only true if t is a positive number. If t is less than 0, then this is y of t, right? Y of t is equal to 0. So you can club both of them and write in this form. Combining both above, You can write y of t as e power minus 5t into e power 3t minus 1 by 3 into u of t. Basically, what u of t is, whenever t is positive, u of t is equal to 1. That will basically give rise to this equation. Whenever t is negative, u of t is 0. So everything will become 0, and that is basically this expression. So both of them can be compactly represented by just one equation given by this y of t. Just multiply this by u of t, and that will take care of both the cases. Fine. So this is the convolution. Okay. Now, like similarly, let's in the same spirit, we will do another question. Question 2. Convolve x1 of t is equal to cos t into u of t, and x2 of t is equal to t into u of t. These are the two signals, and the question is what is y of t is equal to x1 of t convolved with x2 of t. This is the question. Okay, we are going to again use the same definition. We'll do it. Okay, so basically solution answer is as follows. Your y of t is equal to x1 of t convolution x2 of t. And this you can write it as defined by the integral minus infinity to plus infinity cos tau into u of tau into t minus tau into u of t minus tau d tau. Because that's the definite, this is nothing but what? Integral minus infinity to plus infinity x1 of tau, x2 of t minus tau d tau. And I just substituted for values of x1 and x2. Now, by the same logic as above, u of tau is equal to 1 if tau is greater than 0. U of tau is equal to 0 if tau is a negative number. Therefore, this guy will become 1 if tau is greater than 0, 0 if tau is less than 0. So I can make, because in negative axis of tau, this u of tau will go to 0, so entire integral becomes 0. So it is enough if I basically consider this integral as 0 to infinity cos tau into 1, because u of tau is 1 for positive tau. Cos tau into t minus tau into u of t minus tau d tau. Now same thing again, that is u of tau now will take value 1 only if t minus tau is a positive number. U of t minus tau is equal to 1 if tau is less than or equal to t. U of t minus tau equal to 0 if tau is greater than t. So that means again you can consider this integral to grow from 0 to just t cos tau into t minus tau d tau. Why? Because beyond tau greater than t, if tau is greater than t, your u of t minus tau will become 0, and that will kill the entire integral. It will make the integral go to 0. So for beyond t greater than t, tau greater than t, this integral will go to 0. That's why it's enough if you consider just till t. And in the region from tau less than t, your u of t minus tau is a positive number, is equal to 1. That's why I removed this here. That is, it's basically into 1. That's all. Fine. Now it's clear. Now we just need to integrate this. That's all. Okay. So this is nothing but I can write this as 0 to t cos tau minus 0 d tau, 0 to t tau cos tau d tau. Now you see the integral for the first integral, the integration variable is tau, but whereas t is a constant, so I can make it move out of the integral. So this becomes t into integral 0 to t cos tau d tau. But here all are tau, so I cannot move anything outside. So it will be 0 to t tau cos tau d tau. Now what is this? It's nothing but t into sine tau from 0 to t minus integral Now what is this? This is nothing but t sine t minus t sine 0. But sine 0 is 0, so second term will go to 0. So just t sine t. Now how about this term? You need to do integration by parts. You just have to do integration by parts. So if basically, that is, if I have 0 to t tau cos tau d tau, let me call the equation as this is equation 1. Okay, let me just evaluate the second term, 0 to integral 0 to t tau cos tau d tau. Okay, now this by integral by parts, what this is equal to tau into integral 0 to t cos tau d tau minus integral 0 to t d by d tau of tau into integral cos tau d tau. I just applied the integral udv formula. Okay, where basically u is your tau and basically v is your cos tau. Sorry, v is the integral, dv is the cos tau d tau. Okay, that is basically the by parts rule. And so basically, the integral d tau with respect to tau is equal to 1. If you differentiate tau with respect to d tau, it's just 1. And this now becomes tau into sine tau from 0 to t minus integral 0 to t. It becomes sine tau d tau. And that is nothing but tau into t into sine t minus t into sine 0. Again, sine 0 is 0, second term will go off. So it's just t sine t plus cos tau from 0 to t. This is nothing but t sine t plus cos t minus cos 0. Cos 0 is 1. Okay, fine. Now this is correct only if t is positive, because otherwise this integration itself is not meaningless. This integration is meaningless if t is negative, right? Because the upper limit has to be greater than lower limit. Fine. Now this is basically, let's call equation 2. Now I have found, so basically what have I done? I have evaluated this integral tau cos integral 0 to t tau cos tau d tau is equal to t sine t plus cos t minus 1. Now put 2 in 1. Okay. Therefore, put 2 in 1. So what happens is that you see in 1 you have a t sine t, in 2 you have t sine t. Okay, so what will be left out is there's a minus here. So it instead of cos t minus 1, it will become 1 minus cos t. That is the only thing. That is the final answer. The convolution y of t is equal to 1 minus cos t, provided all are positive, t greater than 0. So here also you see this integral is also defined only when t is greater than 0. This integral is also defined only when t is greater than 0. Both the first and second term are defined only when t is greater than 0. For t less than 0, there is nothing, it's not defined, so it's just automatically equal to 0 if t is less than 0. So by compactly representing both of them, we can write y of t equal to 1 minus cos t into u of t, where u of t is the unit step function. Is it clear? Hello? Can anyone unmute and say if this is all fine? Hello? Uh,
Part 2 is not understanding.
Which one? Tell me which one.
Equation 2.
In,
Apart.
do you know
Integrate 0 to t.
this one? Huh?
Yes, sir.
Okay, okay. Basically, do you know integration by parts?
Yes, sir.
Yeah, that only I'm applying. You see, this is like your first function. Cos tau is another function. Call this as u, and this is like dv. Cos tau deta is dv. So it's integral u dv, right? That's what I did now. Basically, integral, recall what is integration by parts? Integral u dv is equal to uv minus integral v du. That's what it did basically. There's nothing else I did. So basically, uv is means what? You need to integrate dv. That is basically integration of cos tau is nothing but sine tau and apply the limits. That is the first function, uv minus integral v du. What is v? Is sine tau. Du means with tau with respect to tau, if you differentiate, it is equal to 1. So it's just sine tau d tau. And then just simplify this, you will get the answer. Is it okay?
Yes, sir. Thank you.
Yeah. Okay, if there are any more questions, you can ask now. Because next I'm going to introduce another way to very geometric way, a very nice way. It's a geometric way to perform convolution. So I think this is the right time to ask questions about convolution if you have any till now with whatever approach I have made. Okay, I don't see any question. Let's move on. Okay, now I'm going to give you another way to perform convolution. Now, until now, what did we do? We just used the definition of convolution integral and we simplified the integral and we found the answer. That is one way, that is a direct way to find the convolution. But there is another very interesting geometric way to view convolution. So I'm going to introduce the So what do we mean by geometric interpretation? Let me now go back to the definition of convolution. Let's say there are basically two signals. X1 of t is, let's say, I'm taking. I'm saying example. X1 of t is something like this. Let's say, okay, and x2 of t is also something like this only. Now, let's say I'm asking y of t is equal to x1 of t convolution x2 of t. What do I mean by that? Integral minus infinity to plus infinity x1 of tau x2 of t minus tau d tau. The main geometric interpretation what I'm going to do is, and x1 of tau is same as x1 of t. The only difference is I made t as tau. So there is no problem with that. But x2 of t minus tau, how does it compare with x2 of t? Simple. How do I obtain x2 of t minus tau? You consider x2 of tau with respect to tau, and then you flip it. You make time reversal. That is x2 of minus tau as a function of tau will look like this. And then you do time shift. That is x2 of t minus tau. Okay, that is the same. This guy has now come somewhere over here. If it is t, this is when t is greater than 0. If somewhere here, if t is less than 0, that is x2 of So see, the y-axis, the x-axis is still tau axis, not t-axis. T is some positive constant, small t, and I'm shifting this. This is my actual x2 of minus tau, and I'm shifting this by a factor of t, either to right hand side or to left hand side. Okay. Now you remember why t greater than 0 means um, left right hand side. That's because if you have t greater than 0, this is same as x2 of minus t minus tau minus t, which is same as um, um, x2 of minus of t plus tau, right? So basically you want, okay, I should have gotten, okay, let me go back this. When will I get, you see this, when will I get x, okay, this one x2 of t minus tau, right? This one is same as saying x2 of minus of tau minus t. What does it mean? I should have delayed my actual signal by an amount of t. Means I need to move it to the right signal, right hand side. That's why for positive value, and this is same as this guy. So for positive values of t, this it means that I'm shifting my x2 of minus tau to right hand side. For negative values of small t, I'm shifting my x2 of minus tau to left hand side. And what I'm doing then? Okay, so this is the graph for x2 of t minus tau. And then what am I doing? I take x1 of tau, which is basically this itself. Oh, sorry, where is it? This itself, but now t changed to tau domain. And x2 of t minus tau, that is basically this function. And I'm multiplying both. Okay, let me multiply both the function and I'm integrating. What does it mean? I multiply both and take the area under the multiplication. If I take the area under the multiplication of these two signals, x1 of tau and x2 of minus tau, that is equal to the convolution value y of t. For different values of delay, right, you will have different values of overlap. The two signals x1 of tau and x2 of t minus tau will overlap differently for different shifts that you give. And this shift is equal to small t. So for different shifts, you basically what you do, you multiply both the signals and take the area under the multiplied signal. Whatever is output of multiplication, that will be another signal, right? This is another signal called y dash of t, y dash of tau. And take y dash of tau d tau integral tau, which is the area under the curve y dash of tau. You need to take the area under the curve. Whatever answer you get, that is the value for y of t. For some other value of t, delay your x2 of minus tau by the same value of t, and then multiply x1 of tau and x2 of t minus tau, and then take the area under the multiplied signal. Now you keep on doing this for every value of small t, you will get accumulate the value for y of t. So this is basically the geometric interpretation or the geometric way to find the convolution of two signals. Are there any questions? Can you tell if there's any doubt? I can handle it now. Okay, maybe let's do some example. That time it will become more clearer. This question 3. Convolve x1 of t equal to e power minus 3t u of t and x2 of t equal to t into u of t using graphical method. Using graphical method. Okay, so let's go do the same thing. Basically, your x1 of t, no problem. Just change the domain t to tau. That's all. Only for x2, you take x2 of tau, you do time reversal, and you do time shift. And different values of time shifts by t will determine the output y at the convolved result at time t. Okay, you shift by an amount of t and then multiply both x1 of tau and x2 of t minus tau and take the area under the curve. That will be the convolved value at time equal to t. That's what we'll do. The first step is basically your x. Okay, for graphical method, you need to know how the graph of the function looks like. If you don't know that, then you cannot do this easily. Okay, so x1 of tau is nothing but multiplied by u of t. That means only for t greater than 0, this u of t will be equal to 1 or it's equal to e power minus 3t. If t is less than 0, x1 of t is equal to 0 because u of t will kill the signal. So the x1 of tau is basically something like this, e power minus 3 tau. It goes to 0 as t tau tends to infinity. What is x2 of tau? X2 of tau is again a linear function, but for negative tau it is 0 because u of t is 0. U of tau is 0 when tau is less than 0. Now what should I do? X of tau you do time reversal. That is basically take the mirror image of your x of tau with respect to tau axis. This is x2 of minus tau. And then what you do? You do time shift by t. Means what? You basically delay the signal. What does it mean? You bring it to some value. Let's say if you basically move this to left, then t will come and sit here. This is when t is less than 0. If you take t to be positive, then this function will go and sit here. T is positive here. Do you agree? Basically what I'm saying is if you shift this signal by a negative number, this will go left. That is basically by an amount of t, and it will end at small t. If you shift this signal to the right hand side, then that amounts to delaying by a positive amount t greater than 0. Okay, now the question is for different values of t, multiply this. So this is basically your x2 of t minus tau as a function of tau. Basically for different values of t, obtain the graph of x2 of t minus tau and multiply with x1 of tau and take the area under the curve. That is all. If you do this, then you know the answer that you have done the convolution. Okay, now tell me for t less than 0, x2 of t minus tau is going in the negative, but x1 of tau takes only positive values. Now, when you multiply both of these signals, what will be the output? Yes, can anyone answer?
Maybe 0.
Correct. Because this x2 of t minus tau takes the value 0 in all positive tau axis, but x1 of tau takes the value 0 in all negative of tau axis. There is no common overlap between these signals. So when you multiply them, it will become 0. Therefore, for t less than 0, your x1 of tau into x2 of t minus tau is equal to 0. Or if you take the area under the curve, x1 means integrate from all the way from minus infinity to plus infinity, x2 of t minus tau is also 0. Therefore, your y of t is equal to 0. The convolution value y of t when t is less than 0 is equal to 0. Now let's take for t positive. Means what? You recall your x1 of tau is looking something like this. Okay, this is e power minus 3 tau and this is tau. And your x2 of t minus tau for t greater than 0 looks something like this. This is your t. After t, it is becoming 0. Okay, now if I multiply both of them, maybe I'll just move this to bit left. If I multiply both these signals, what do I get? x1 of tau into x2 of t minus tau. For basically in the negative tau axis, the x1 of tau is 0. So all these guys will become 0. And in the positive tau axis, beyond t, the x2 of t minus tau will become 0. So that in that particular value, x1 of tau, doesn't matter whatever value it is, the multiplication will become 0. The only finite overlap is between 0 to t. So the multiplication will look something like this. And between 0 to t, this is like a linear function. So this is like, it's just like a multiplication by, um, it's like multiplication by 1. It's like because it's a linear slope. Oh, not really. Oh, not really. What is the equation of this line? Is nothing but t minus tau, right? The equation is nothing but t minus tau of this line. This equation is e power minus 3 tau, and this equation is 3t minus tau. So in this, if you multiply both, it becomes e power 3t minus 3t into t minus tau. Do you agree? Please, this is a very crucial step. If you don't understand, tell me. All it is very simple. I wrote down the equation of this line till t, and I wrote down the equation of this line, which is given by e power minus 3 tau. When you multiply, it only takes non-zero value between 0 to t, and that multiplication is just a multiplication of equation of these two lines. Any doubt till here? It's very important you ask me now, otherwise the subsequent problems will also be might become difficult to understand. Yes? Or can anyone tell if it's okay? If it's okay till here? Yes?
Linear function multiple by exponential is always exponential.
Sorry, I'm not able to hear you properly. Can you repeat?
Linear function multiplication with exponential is always exponential.
No, it need not be exponential. Maybe it will be, yeah, correct. You figured out a good point. It need not be exponential. It will be some other graph. Maybe not sure. Um, maybe something like this. I don't know. Maybe let it be some graph. Doesn't matter. We don't need. Can be some arbitrary, but it will take the value non-zero only between 0 to t, and the value is given by the multiplication of e power minus 3t and t minus t. Is that okay at least?
Yes.
Yeah. Okay, that's all. So this is now you once you do, then what is the next step? Take the area under the curve. What is the area under the curve? 0 to t, e power minus 3 tau. Okay, 3t. Sorry, it should be okay 3 tau, right? Because this is because this is e power minus 3 tau, so tau should be maintained. E power 3 tau, 3 tau into t minus tau d tau. Okay, let's again do this. This is basically your convolution y of t. So y of t equal to, I can write this as 0 to t e power minus 3 tau d tau minus integral 0 to t tau e power minus 3 tau d tau. This is t into e power minus 3 tau by minus 3 from 0 to t. And this is, okay, let me just write it out like this, tau into e power minus 3 tau d tau. Now this is nothing but t into e power minus 3t minus t by minus 3, because e power 0 is just 1. And now here it is integral 0 to t tau into e power minus 3 tau d tau. Now again, this is basically like of the form integral udv. So apply integration by parts. IBP means integration by parts. You do this as a homework, and you can show that the resulting, after doing integration by parts and substituting in this equation, you can show that this becomes t by 3 plus e power minus 3 t by 9 minus 1 by 9. You can show that this will come out to be this answer. But all these things are valid when t is positive. Therefore, you can write compactly, you can write it as, therefore, compactly, we can write y of t equal to t by 3 plus e power minus 3t by 9 minus 1 by 9 into u of t. Okay, this is basically the geometric way to perform the convolution between two signals. What is geometric way? You do time reversal and then you shift it and then you slide. Okay, let me tell you the terminology more simply. What did I do here? You see, basically you flip it, you get it, and then take the signal and slowly slide from the left. As you keep sliding means for each instance will be for different values of small t. What did I do? This is T1, T2, T3, T4, T5. I kept on sliding this x2 of minus tau. For each values of such sliding, I realize this is x of t5 minus tau, x of t4 minus tau, x of t3 minus tau, x of t1 minus tau. Here t1, t2, t3 are positive numbers, t4, t5 are negative numbers. That is how you should do. And that is basically what you do is you keep the first function constant, take the second function, do time reversal, and then keep sliding this time reverse function from negative all the way from minus infinity to plus infinity. And for every slide you do, take the multiplication and take the area under the multiplied curve. Once you got the value, move to the next slide. Slide to another variable, another t, then multiply the two signal and take the area. Like that you keep on doing from minus infinity to plus infinity. Whatever result you get, that is the convolution value for each such slide you do. This is the geometric way to interpret the convolution operation. Okay. Okay, we will actually do two more such questions using convolution using this geometric interpretation. Then you will be more comfortable with this geometric way to convolve two signals. Okay, I think we are at a good time to take a break. Let's take a break till 7:20. It's 7:08 now. Let's take a 15-minute break. So it will be till 7:23. Then we'll again resume problem solving at 7:23. All of you can stay online. You don't need to leave the call, but just take some break for 15 minutes. Okay, I see some chart. Convolution problems 8 and 9 of assignment. Okay, so maybe let's do that next time. I will look at the question and come back. Okay, so let us resume. So we are at question number 4 for today. Okay, so question number 4 goes as follows. Same convolution question. Convolve x1 of t equal to e power minus at, but t ranges from 0 to capital T, and x2 of t equal to 1 when t ranges from 0 to 2t. Simple question. So let's draw the figures of both. Answer. So if you draw x1 of tau, it from 0 to t alone, right? It is e power minus a tau. This is a graph of x1 of tau. And let's move to x2 of tau now. X2 of tau is rectangle 1 from 0 to 2 capital T as a function of tau. Now what's the first step? First step, make time reversal. I'll just time reversal. That is, take the mirror image of the x2 signal with respect to the y-axis. Tau, and it is x2 of minus tau. Minus 2t is 0. This is x2 of minus tau. And then what you do? Time shift. What do you get? You get something like this. Minus t, 2t minus t. Minus 2t minus t. This is for t less than 0. Okay. This is 1. This is x2 of t minus tau. Okay. And now what should you do? This one, this box, basically it's a box, right? Rectangle, I need to keep sliding through. For every slide step, I need to multiply with x1 of tau and take the area under the curve. Then slide through another next step, multiply, take the area under, and then keep on sliding. For different positions of these boxes, you will get different overlaps. And then you multiply them and take the convolved answer. Okay, so let's consider t less than 0. First we'll start with t less than 0. For t less than 0, x1 of tau is this one, e power minus a tau d tau, a tau, x1 of tau, and x2 of t minus tau is something like this, minus t minus 2t minus t. Now tell me, what is the product? What is the product? Yes. Yes, it is 0 because there is no overlap. So equal to 0. Multiplication is equal to 0. Therefore, area under the curve is also 0 because there's no curve actually. It's full 0. Therefore, y of t is equal to, that is the convolved value, is equal to 0. Now let me take the scenario t between 0 and capital T. That is, t is greater than 0, but it is less than small t. That means what? This is how the scenario looks like. You have basically x of x1 of tau. Tau is e power minus a tau up to t. This is x1 of tau. And your x2 of t minus tau is basically looking like this. It just crossed the y-axis, but it has not gone beyond t. Sorry. Okay, this is how the graph of x2 of t minus tau looks like when t lies between 0 and capital T. Now when you multiply both, what do you get? This is equal to 1. You get this. Do you agree? This is correct. That is, the overlap is basically, this is the overlap. You see, let me draw it. The overlap is only this much. Only in this region, the multiplication will yield. Let me even draw it, no problem. Only this is the overlap region. So the multiplication will be non-zero only in this overlap region. And in this overlap region, this guy is taking equal to 1, and this signal is e power minus 8 tau. So 1 into e power minus 8 tau is same as e power minus 8 tau. Okay. So basically now then basically what you need to do, take the area under the curve. Area under the curve is what y of t is equal to integral 0 to t e power minus 8 tau d tau, which is equal to e power minus a tau by minus a from 0 to t, which is equal to e power minus at minus 1 by minus a, or 1 by a times 1 minus e power minus at. Minus a capital small t, not capital T, small t. Fine. Next scenario, when t lies between capital T to 2t. Then what happens? Let us draw. X1 of tau will look like the same. Tau t 0 e power minus a tau. But your x2 of t minus tau, tau will look something like this. See very carefully. This is basically t, and somewhere 2t is here and t is basically here. Why is it possible? Because see, this width is smaller than this width. In fact, this width is only half of the rectangle width. That's why it's possible that whenever t, small t lies between t and 2t, the entire rectangle will be will cover the width of this exponential function. Okay, if this is t, then what is this? You can do it, right? T minus 2t. This is t minus 2t. Now, what will be the overlap area? The entire thing. This is the overlap. This is x2 of t minus tau. If you multiply both, what do you get? You get this one. From 0 to capital T, you get the entire exponential function. X1 of tau into x2 of t minus 1. And that is equal to x1 of tau itself. Because you're just multiplying by 1 in the entire interval. E power minus 8 tau. Okay. Therefore, area under the curve is what? Y of t equal to integral 0 to capital T now, not small t, e power minus a tau into 1 d tau, which is same as, you can say this is 1 by a into 1 minus e power minus a capital T. Now next case, when t is between 2t and 3t, what will happen? You see, very carefully observe. X1 of tau is same, e power minus a tau till t tau, but x2 of tau, t is greater than 2t, t is greater than 2t, but less than 3t. Means let's say your t is some, so let's say this is t, this is 2t, and this is 3t. So your t, this is where your t is. So the x2 of t would have started here, but it will end here itself because this width is only 2t. This width is only 2t, so this transition will happen even before it goes to 0. That is, there will be some gap between this y-axis and this transition. There will be some 0 region, right? So this is one only between here to here. In this small region, x2 will take the value equal to 0. Because this width is only 2t. It's only 2t, and I'm saying that small t is greater than 2t, which means there will always be this. In fact, exactly this amount of by t, this about the width of equal to small t, you will be having a 0 amplitude. So you can, what is this value? This is exactly t minus 2t. This value, t minus 2t. So tell me, what is the area of overlap now? It's only this much. This is the area of overlap. This is x2 of t minus tau. So if you multiply both, what do I get? Tau, you get something like this. Till t minus 2t, e power minus a tau, x1 of tau into x2 of t minus tau. So what is the area under the curve? Integral t to t minus 2t to capital T, e power minus a tau into 1 d tau. And you can show that this is equal to 1 by a into e power minus a of t minus 2t minus e power minus at. This is basically your y of t. Now, final case, when t is greater than 3t. In this case, what will happen? Your x1 of tau, the function of tau is the same, e power minus a tau till capital T, but your x2 of t minus tau will be looking like this. 3 is greater than 3t, right? So you see t, 2t, 3t, and your t is somewhere here. So now this guy, this rectangle end will, sorry, this rectangle will end before, after capital T, not before capital T, because this width is only 2t. Because you see, go back to the first figure, is equal to 1 when t less than 2t. So this width is only 2t. That's why this, when small t takes a value greater than 3t, the first transition, the minimum value of t for which it takes a value equal to 1 is more than capital T. Now what is the overlap? What is the overlap? No overlap. So when you try to multiply, you will get 0. Therefore, again, your convolution area under 0 curve is equal to 0. Now let us summarize under different curves. Basically, what did we show? That your convolution y of t takes the following values. It's a split function. 0 if t is less than 0. Okay, that is basically the first case. You go back here. Whenever t is negative, you don't have any overlap between them. So our convolution is 0. That is basically when the rectangle was very, very left to leftmost edge. Now you slowly slide this rectangle so that it enters the region of overlap between x1 of tau and itself. So it encounters some overlapping, and then you will, and then you keep on sliding it. And once this you've slided enough that this small t now exceeds capital T, then you will be in this region where there's a complete overlap of x1 of t and x2 of t. So you get full overlap, and then you take the area under the full multiplication. And now what happens when you then further slide such that the small t exceeds 2t, then what will happen? It has some part of the box will now not overlap. This is basically a non-overlapping region, so only a part will overlap. And now when you slided the box 2 away, that there is no overlap at all, the convolution again goes back to 0. So this is the geometric way to interpret how convolution happens. Essentially what you do, fix the first function, take the second function, do time reverse, and then keep sliding the second function from minus infinity towards infinity. And as you keep sliding, keep checking how much it overlaps and take the area under the overlap. Okay, take the area under the multiplied version of the two signals. And at each slide value, whatever is the area of their multiplied value, that is the convolved value. at time instant equal to that sliding value, like small t. Okay, so I'm just going to summarize. We have done for different values of sliding windows. Whenever you have not t is less than 0, convolution is 0. Whenever t lies between 0 and capital T, the convolution is this number. Whenever t lies between capital T and 2t, the convolution is this number. Whenever t lies between 2t and 3t, the convolution is this number. And when t exceeds 3t, the convolution again goes back to 0. So that's what I'll just quickly summarize. So 0 if t less than 0, 1 by a times 1 minus e power minus a cap small t if t lies between 0 and capital T. Sorry. 1 by a times 1 minus e power minus a times capital T if t lies between 2t and capital T. 1 by a times e power minus a of t minus 2t minus e power minus at if t lies between 2t and 3t. And finally, it goes to 0 if t exceeds 3t. Was this any doubts in this example? This is the convolution value. So convolution is another signal. It takes whenever the time at which you negative number, the signal takes 0 value. It takes between 0 and capital T, it takes this value. So it's a function. So you see it's a at. So it's a function of t. Whenever the capital this time takes between t and 2t, it is this value. Here this is independent of small t, so it's a constant. Whenever it takes between 2t and 3t, this is this value. And whenever t takes greater than 3t, it takes 0 value. So this is a convolved signal, convolution output. So are there any doubts here? This is the right time to ask me the doubt if you have. Yes. If there are any doubts, you can ask me now. Okay. So there are no doubts. I'll go ahead. Okay. So one more question we will do on convolution, same graphical method, and then we'll move on to next for the different varieties of question. Okay. Next question is actually very interesting because it's very oftenly asked in GATE questions, in GATE exams. So question number 5. Convolve the following signals. Okay. Your x1 of t looks like this. From 0 to t1, it takes a value 1. Your x2 of t looks like this. T same as 1 only, but from 0 to t2, where t2, t1 is greater than or equal to t2. So you need to convolve to this called a rectangle signal because it's just one rectangle between some non-zero interval. So here it is from 0 to t1, here it's from 0 to t2. It's a rectangle signal with unit amplitude. I'm asking what is the convolution of these two signals. It's a very interesting, it has the final answer has a very interesting interpretation. So let's try to convolve these two signals using graphical method. Okay, same whatever we did just now. Okay, answer. First thing is just transform the t domain to tau domain. X1 of tau, it looks like this. 0 to t1, tau 1. Now what you do? X2 of tau can transform t2, x2 of tau is a function of tau and 1. First step is what? Time reversal. So what you can, you take the mirror image. Becomes like this. Minus t2 0, x2 of minus tau, and it is amplitude is still 1. And what you do is shift by t. And if it's a negative shift, then it looks like this. This is basically t, and this is minus t2 minus t. Okay. So, okay, I think it's plus t or minus t. Yeah, no, it's plus t because anyways t is already negative. So this is for small. The t is already negative. So this is basically x2 of t minus tau. Okay. Now what I need to do? For different values of small t, this box will be at different places. I need to slowly slide this box from minus infinity to plus infinity, and then multiply with x1 of method. Okay, so let's first what we do. We will first so here you see I divided into five. Oops, sorry. Here you see the previous question I divided this into 5 intervals. How did I know this? By first analyzing the sliding different overlapping scenarios. What are the different overlapping scenarios? First, I analyzed that, and based on that, I divided the solution into 5 different intervals, and then I computed the convolution values. Right. So first step is to understand what are the different sliding scenarios. Okay, sliding scenarios. Okay, so basically the first is basically as follows. You have x1 is here and x2 is here. It is sliding. Okay, this is of duration t2 and this is of duration t1. Okay, this is the first scenario where there is really no overlap. Okay, maybe the second scenario is like as follows. Now remember, t1 is greater than t2. That is, this width is more. Maybe I will draw it slightly bit wider. Okay. T1 is greater than t2. The next scenario is when something like this. X1 is like this, and x2 has just started to enter. Okay, maybe I should give a different color to this also. This is x2. I'll draw here also x2. Okay, so you see there's an overlap. This is the second scenario. Next scenario is what? This is what again? This is T2, and this interval is T1. But remember, T1 is greater than T2. That's a given in the question. So then the third scenario is basically as follows. X1 is here, and your X2 will be here. It's completely inside. This is X2. So it's completely inside X1 because T2 is greater than T1. So you can accommodate the entire X2 inside X1. Now the next scenario is as follows. See it very carefully. X1 is this, but X2 has slided so much that a part of it is only inside, a part of it has gone outside. Then the overlap is only this much. Okay, maybe everywhere denote this by sliding. I'm sliding this blue box from left to right. And finally, it so much that X1 and X2 are completely again non-overlap. No overlap. Here also no overlap in the first thing. There are how many scenarios therefore? This is scenario 1, scenario 2, scenario 3, scenario 4, and scenario 5. So there are going to be again 5 intervals in which the convolution values will take different split functions. Similarly, here also you see there were 5 scenarios, right? 1, 2, 3, 4, 5. Similarly, here also you have these 5 types of scenarios. Okay, you need to find the convolution value for each of these 5 scenarios, and that's what we will do now. Okay, for case scenario 1. Scenario 1, what is happening? When both are non-overlapping. When will this happen? When your small t is less than 0, your scenario is something like this. Maybe I will, okay, let me write it down. Small t less than 0, your x1 of tau is like this, 0 to t1, and your x2 of t minus tau is something like this. It's away. This is with t2. This is my t. What is the output? If you multiply both, you get y of t equal to 0 because there is no overlap. Now, when you go to the next scenario is what? When this box has just come near the x1 box and it just started to slide. Okay, there is a small overlap. That is what when will this happen? You should have non-overlapping phase and overlapping phase. This will happen until some values of small t. Once the small t exceeds this, it will completely come under the full box. So what is this value? Scenario 2 is basically where your t is greater than 0 but less than t2. Why? If your this t is more than t2, then the entire width of the x2 will come inside x1 because t1 is anyway greater than or equal to t2. Then this will be in scenario 3 where the entire x2 box is inside x1 box. But I don't want that to happen, right? Because I'm still in scenario 2. So that's why your t should be greater than 0 but less than t2. In this case, how will your boxes look like? Your x1 of tau will look like this. It will be same as t1, and your x2 of t minus t2 will look t minus tau will look like this. So what is the overlap? This is the overlap. So if you multiply both, you will get what? This is x1 of tau into x2 of t minus tau. A very small, again, one, this is all amplitude is 1. So 1 into 1 is 1, but 1 will be from 0 to t, only from 0 to t. Therefore, area is what? Integral 0 to t, 1 into 1 d tau, which is equal to t itself. Now let's move to case 3, scenario 3. What is scenario 3? Your x2 rectangle is completely inside x1 rectangle. This will happen if your t is greater than t2, so that you have brought the x2 box inside x1 box, but it is not too high that it is more than t1. If it's more than t1, then you will enter of x2 will be outside the x1 box. I don't want that to happen. This is your t1. You don't want your small t to be more than t1. At the same time, you want your small t to be greater than t2 so that you brought this left-hand transition inside x1 box. Okay, so that is basically scenario 3, where your t lies between t1 and t2. Then in this scenario, you will look something like this. x1 of tau will be 0 to t2, so t1, and your x2 of t minus tau will look like this. Okay, and what is the overlap? Full overlap with x2. So if you look at these limits, this is at t and this is t minus t2, because this width is only t2. This width is only t2. That's the width of the x2 box. So if you multiply both, you get what? You get like this, t minus t2 to t, and t1 is somewhere here. And 1 into 1 is 1. Therefore, if you take the area, you get integral t minus t2 to to t d tau, 1 into 1. So this is nothing but, you can show that this is nothing but t minus t plus t2 equal t2. Final scenario, scenario 4 is when your x2 box has gone outside. The x2 has gone outside x1, but a part of x2 still remaining inside x1. Okay, when will that happen? If your small t is more than t1, but not so much more that this left also has gone outside. Correct? That is, your t should be less than t1 plus t2, but should be greater than t1. This is a scenario under which scenario 4 will happen. Okay, so that is t should be less than t1 plus t2 and greater than t1. In this case, your x1 of tau will be like this, 1 from 0 to t2, and your x2 of t minus tau will look like this. And what is the overlapping region? This will be the overlapping region. And so when you multiply, what you get is as follows. This is t, and this is still t minus t2. So integral t minus t2 to t1, right? Because the overlap is until this guy, t1. Okay, this is t1. Your x1 is t1, right? Yeah, x1 is t1. This is until t1. So it's from t1. T1 is the upper limit, and t minus t2 is the lower limit. Okay, 1 d tau. All x-axis are tau axis. Okay, remember that. This is x1 of tau into x2 of t minus tau. This is nothing but capital T1 minus small t plus t2. Now, final scenario 5 is when your small t is greater than t1 plus t2, in which case this x2 would have gone completely outside x1. There is no overlap. So if you multiply, it again becomes 0. T is greater than t1 plus t2, in which case no overlap. So your y of t will be equal to 0. So what we'll do, let us summarize all of them. Summarizing. Your y of t takes the value as follows: 0 if t is less than 0, t if t is between 0 and t2, t2 if t is between t1 and t2, t2 and t1, t1 plus t2 minus small t if t is between t1 and t1 plus t2, and again 0 if t exceeds t1 plus t2. Okay, this is the convolution value. But now, if you draw the graph of y of t, you know how it looks? Okay, let us draw the graph of y of t. So the splits are at t2, then at t1, and at t1 plus t2. Between until t less than 0, you have no output. So everywhere 0 output. From t between 0 to t2, you have a t. Y of t is equal to small t, and it goes until t2. So let's say this t2. So it goes till like this. Now from t2 to t1, the output is constant at t2. So it is like this. And from t1 to t1 plus t2, the graph is t1 plus t2 minus t. You can show that this graph is like this. And beyond t1 plus t2, your y of t is 0. And what is this? This is nothing but a trapezium. So the convolution of two rectangle signals is a trapezium. Okay. Now, okay, special case. If t1 equal to t2, that is both the rectangles are of equal widths, then what will happen? These two will be same, they will coincide. this T1 and T2 will coincide. Then what will happen is this graph will be nothing but T2 equal to T1, nothing but a triangle is 2T. This is at T and 0, where T is equal to T1 equal to T2. And amplitude is also T. Okay, this is what? A triangle. Because when T1 and T2 are equal, this width will, this is a 0. And both the points are equal, so it will go and then come down. Okay, you can see here also. If T1 and T2 are same, you will not have this. It will 0 to T, it will increase first. It will increase first, and then again it will decrease. So it's a triangle. Okay, maybe as a first cut exercise, what you can do is you do one thing. You first go to the exercise here itself. You assume T1 and T2 are same, and then do the same all these procedural or sliding graphical method and verify for yourself that you're getting a triangle. Okay, so from this, the inference is as follows. Very important gate exams. Okay, conclusion. Convolution of two rectangle signals with a unequal widths gives a trapezium, and B equal widths gives a triangle. What do I mean by unequal widths? That is, you see, go back to the exercise. This is the width of x1 is t1 and width of x2 is t2. When t1 is not equal to t2, that is both are unequal, then the convolution of this x1 and x2 will lead to a trapezium. However, when widths are equal, that is t1 equal to t2, then the convolution of these two signals will give a triangle. That is what this result is saying. Okay, fine. I actually had planned for two more questions, but I think let's not do it hurry. Let's do them in the next class. But I think it's now already 8 p.m. Maybe it's the right time to stop. But we can, if there are any doubts based on what we have seen till now, you can ask me now. If there are any doubts, please unmute and ask. Yes, are there any doubts? Can anyone unmute and say if everything was okay? If everything is clear?
Okay, sir.
Okay, great. Okay, fine then. Nice. So today I think we dealt spent quite a bit of time on understanding convolution, but it's good. Convolution is very important to signal systems. You should be very comfortable in doing convolution operation. We have seen two types of two ways to do convolution. One is the by definition, and other is via graphical method. And this graphical method will become very useful if you're able to visualize, if you're able to draw the graphs of the signals. Be very easy. So you see, we just did by nice geometry and stuff. We didn't deal with that too complicated integral expression for convolution. Okay, so let's stop for today then, and then let's meet next week again. Thank you.